Hello and welcome back to the next installment of Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, the instructor on Chapter 4, Lesson 5. We'll be going over how to analyze a statical curve of stability. So you've seen in the previous lessons that when I draw these generic curves of statical stability, there's a dip in the curve at smaller angles. So let's look at one right now. Here in the black, we see the curve based on the assumed kg, the assumed center of gravity. Now, with this dip, we know that sine starts at a minimum at 0 and then goes to a maximum at 90. But what if the sine correction actually goes above this dip at these low angles? Well, this will cause a curve that looks just like this right here, where it's actually a dip that goes negative and then positive. Now, what does this dip have to do with anything? Well, we know that we have to take the value of our sine correction and subtract it from our original curve. So right here, if we use dividers, we know that this value here is from the axis up to our sine correction. And if we subtract that from this point here, we would get a dot below the axis, which would mean this value here would be negative. What does that mean? That means that if we define our moments again as positive going counterclockwise, a negative moment or a negative writing arm would impart a negative moment, which would be going clockwise, meaning that a ship that is inclined at this angle right here would have a moment that's trying to cause it to go further clockwise. It'd be causing an upsetting moment. If we draw out this new curve, which looks something like this, we see that from this point 0 up to this point where the curve recrosses the horizontal axis, we always have negative moments. So it's always going to be upsetting to this point. And we're going to assume this is towards starboard. Then on the right side of this line here, we see that the values are positive. And going with this orientation, we know that positive is counterclockwise, which means that a ship that keeps going further over has moments that want to kick it counterclockwise back to a point. So at this point here, this dotted line, if we go a little bit to the right, so incline a little bit past that, we have moments that want to kick us back in the positive direction. And then a little bit negative, or a little bit to the left of it, there's moments that want to kick it over back in the upsetting direction. So if a ship is right at this angle, there's not going to be any writing moments on it. So it's just going to look like it's listing. However, because we have a negative GM situation, when we cause a sine correction, or that rise in the center of gravity, that's so great that we actually have negative values for our original writing arms. We have that negative GM, so we're actually lolling. And remember, in the previous lessons, we saw that the statical curve of stability is actually mirrored along this axis right here, this axis and this axis. So if we take the sine correction and continue it all along this way, we would see that the curve actually lolls in both directions. So the curve actually crosses 3 different times this main axis. It'll cross here, it'll cross here, and then it'll cross one more time right here. The curve will take a shape like this, cross again, that'll be the opposite angle of loll, which is the exact same value as this angle of loll, and then it'll just continue the same shape as we see over there, over on this side. Now I mentioned we have a negative GM situation. How can we tell that on the curve itself? Well, we can just use our radian line trick. Right here, you see the curve dips down, comes back up, just like what I have right here in this generic example. Then if we linearize right along that 0, so just take that line, how it acts from 0 to 1 to 2 degrees, and just carry that all the way out, it's still going to hit that 57.3 line, but this time its value is going to be below 0, which means it's going to have a negative GM. That value directly tells us what's going on, or that's the initial stability for a ship that has an overall curve like this. All right, next up, we're going to talk about deck edge immersion. And deck edge immersion is something that can happen when a ship is rolling or listing. And there are completely different consequences if a ship immerses its deck edge while it's rolling or listing. So let's take the first case where the ship is rolling. We're going to use this diagram here, and it's going to be in the inertial frame, like I had mentioned before. So we're going to keep the ship constant, and we're going to have the water line move about the ship. So when a ship is rolling, we're going to assume the center of gravity is directly on the center line of the ship, and there's no damage taken. The ship is just doing normal underway steaming. Now when the ship rolls, so we go from waterline 0 to waterline 2, we notice that when the deck edge is immersed, we have a little bit of water that we can consider as a weight addition to that ship. With pressure, I had mentioned before that hydrostatic pressure from water always acts normal or perpendicular to a surface. So even though gravity is pointing that way, the pressure of the water is actually pointing directly against the hull. So if we consider this like a weight addition, then that means we have to do, or we see that the center of gravity is going to shift over a little bit and also up a very minuscule amount. So when we do a cosine correction to the roll, and this is only when the ship is over at waterline 2, we're going to have a cosine correction that looks very non-consequential. It's not going to affect the stability of the ship very much at all. And if you have any experience on the ocean, you'll notice that sometimes your weather deck can dip underneath the surface of the water, but what happens? The ship just springs right back up because the ship hasn't lost its righting arm when it goes over to 10 degrees, 20 degrees, 8 degrees, whatever it might have gone over to in that weather. Now, let's take a look at the same thing, what happens when we immerse our deck edge from listing. All right, so now let's assume that our vessel has hit some rocks and we've flooded some off-center compartments or maybe tanks, and now the center of gravity has shifted horizontally an extreme amount. So going back to this diagram, we have the original center of gravity here, and it's going to move over some distance to G1. Well, we know that doing a horizontal shift in G means it has to do with cosine correction. So let's go down here to the list case. If this is a very serious occurrence, so if we take on damage, it's going to be a relatively severe cosine correction. So we'll have something that looks like this, a very consequential cosine correction. Assuming that this point of vanishing stability is 90 degrees, they would both meet at 90. Now, if the ship continues to list, eventually it's going to, well, if it continues to list, that means it's taking on more damage. So if we assume the list is only due to an off-center weight, we have G going further and further over, maybe to G2, which means we're imparting more and more and more of a cosine correction. So going from there to there, and even further to there. Now, as you noticed, and you probably realized from previous lessons, we're diminishing all of our reserve buoyancy here under this curve. So right now, the ship only has like this much buoyancy that it can react to. Now, if there's sine corrections on top of this, the sine corrections would probably be looking like this. So now the ship only has this much buoyancy to work with. However, you notice that there is one spot on the curve that's always going to be above these lines, and that's that angle of maximum righting arm. Now, what happens if that angle of maximum righting arm is covered up by a cosine or a sine correction? Meaning that this point gets covered up by maybe a cosine correction like that. We're going to take that curve of stability and actually see what happens. So now we've listed well past the danger angle, and we've listed past that angle of maximum righting arm. So we had talked about before how this inertial frame gives us hydrostatic pressure that we can kind of assume or model as a weight addition, a little bit high and then all the way to the side. This weight addition here, if we're listing, is going to cause the center of gravity to move a little bit more to the right, which means it's going to go a little bit further here to G3. But then with that shift in center of gravity means that now we have to list a little bit more. If the ship lists a little bit more, that means the waterline is now going to look like this at waterline 3. Which means now we're adding even more water to it here. So now we've added this much water, which means there's going to be more force pushing down on that deck edge, which means more of a weight addition, more movement of the center of gravity, means more listing, and more loss in stability. So once you list to your angle of maximum righting arm, this kind of cascade of adding water, shifting center of gravity, and then listing even more occurs. And eventually the ship is going to have such a moment that it will eventually capsize. That's why we give ourselves that buffer of time that we refer to as the danger angle, which is half of the angle of maximum righting arm, so that we don't hit this catastrophic event of deck edge immersion when we're listing. So next up, we're going to take a look at cosine corrections for vessels that have a point of vanishing stability past 90 degrees. So it might be 95, 100, 110, whatever it might be. So here is a generic statical curve of stability for a vessel whose point of vanishing stability is beyond 90 degrees. Now we know the behavior of cosine. Cosine starts at a maximum at 0 degrees. It goes to 0 at 90 degrees. And then beyond 90 degrees, it actually carries on into negative numbers. So, cosine with theta greater than 90 degrees is less than 0. It just means it's negative. So, if we go back to our cosine correction, if GZ1, which is our new righting arm, equals GZ0, which is the original righting arm, right up here, minus GG2, which is the distance that the center of gravity shifted horizontally, times the cosine of theta. If cosine of theta is negative, GG2 is going to be positive. That means we're subtracting a negative number, which means we're actually adding a number. So GZ1 is greater than GZ2 at theta is greater than 90. So let's take this example. We're going to impart a catastrophic cosine correction onto this vessel. So let's say, let's go with red. It starts up here. It goes down. Crosses at 90, and it actually goes like that. Now we do exactly what we've learned before. We know that right where cosine crosses this curve, that's going to be our angle of list. So it's going to go right here, because the value is going to be 0 at that point. Then at 90, we know that there's not going to be anything we subtract from the original curve, because the cosine of 90 is 0. So we find where that righting arm is at 90 and draw that point. Then everything down here, instead of subtracting it or going lower, we actually have to add it. So the new curve of stability is actually going to look like that. Something right along there. So this would be our cosine correction along here. Extending it past 90, we go into the negatives. Then we go from our angle of list, where they cross each other, because subtracting the cosine correction from the original curve would give us 0. That is 0. And then it's rising here. At 90, there's no change from the original curve. Then it increases further. Now, no matter how catastrophic that shift of weight is, for example, in car carriers, when they lose their cargo, there's an extreme shift of all that weight of the cars over to one side, be it port or starboard. So let's impart an even more catastrophic cosine correction. Let's say it starts way off the top of the screen and it comes down, say something like this. So very extreme, like that, and pulls off way down there. Now we do the exact same thing. We know that they cross right at this point. So our angle of list would be right around there. At 90, there's no difference. Now, it seems like there is just some kind of playing on the behavior of cosine, but you can draw a diagram for yourself. Draw a ship that has a center of gravity right along the center line, inclined over 90 degrees, and then draw the same ship inclined over to 90 degrees, but this time have a horizontal shift in center of gravity. You're going to see that there's no change in the righting arm of that ship. The center of buoyancy is going to be in the same spot. So by knowing that, we say, okay, it makes sense now that the change in the righting arm is going to be nothing at 90 degrees. So for this even more catastrophic event, we have our righting arm right here. And then it's just going to continue off faster and faster. So we're going to go from our angle of list right through that point. Now we see with this more catastrophic event, we have a stronger angle of list. That's why you see vessels like car carriers, when they lose their cargo to one side, they typically they settle in at lists right around 60, 70, 80 degrees. It's all because of these cosine corrections. They meet at these strong angles. However, there's no change in the righting arm at 90 degrees. So that ship is actually built to withstand such a catastrophic cosine correction. There are many ships out there can't. There's this a special shape of the hull that allows the ship, and also watertight integrity, to allow the ship to actually survive a huge change in the center of gravity due to that shifting weight. All right, now last in our outline here is using the radian line trick that we learned in lesson 2 of this chapter for a sine corrected versus a cosine corrected curve. Now, we know that sine theta can be approximated as theta at angles right around 0 degrees. So we can only make that assumption that I derived in lesson 2 if we're dealing with angles very, very, very close to 0. So now let's take a look at sine corrected curves. We know that with sine corrected curves, we have to subtract our correction from the original chart, or from the original curve. However, with sine equals 0 at 0, and it equals extremely small values very close to 0, which means we're not making much of a correction onto that curve, which means we are always going to be starting right around 0. So it's possible for us to linearize our chart based off of this assumption that we make sine of theta approximated as theta at angles right around 0. So if we do that, we have this solid line being our original curve, and then our sine corrected curve being right here. So we know that right at 0, there's not going to be any change, minimal change at small angles, and then the maximum deviation is going to occur at the very end. So here, we are able to extend our lines out to that 57.3 degree line, and get here this solid red line corresponds to this solid black line, the original case. And if we shifted our center of gravity up, we know that we would have subtractions in our sine corrections, so all of our righting arms would be lower. Right here, this dotted line shows just that, and this dotted red line shows a lower GM, or a smaller GM, than what we had with our solid line. So we know that a sine correction is done with a vertical change in the center of gravity. If we lift that center of gravity, so if we reduce our GM, we know our righting arms are going to get smaller. Right here, we see that our righting arms are smaller after we did our sine correction, and we see through the application of the radian line that our GM has in fact gone from here to here. So this is a good example of using the radian line. Now, what happens if we try and use it for a cosine correction? Looking at this cosine corrected curve, we see that the ship is going to have an angle of list, and we've talked about that before. Cosine is a maximum at 0, it's 1 at 0, and then it's a minimum at, it equals 0 at 90 degrees. So we're taking a lot away from the origin, and then slowly converging to some point. So right here, we know that we can only linearize sine theta into just theta at angles right around 0. And when I say right around 0, I mean 0 to 3 degrees maybe. So here we have our original curve, and we have a proper execution of the radian line. on this top line. Now, if we cosine corrected that curve right here, this is an improper use of the radian line, because right here, this angle is nowhere near the origin. It's nowhere near 0 degrees. So for a cosine corrected curve, you cannot use the radian line. For a sine corrected curve, you can. Now, does that mean that a ship that has an off-center center of gravity cannot have that radian line trick used? No, it doesn't. I'm going to show you here in a second. To demonstrate this, let's take a look at this diagram. So we have two vessels, and there's nothing different between them except the location of the center of gravity. So the heights of the center of gravity are the same. The height of the metacenter is the same. However, the center of gravity on the right side is pushed all the way to starboard, whereas on the left side, we have the center of gravity directly on the center line. Now remember, the height of the metacenter is just the vertical distance between G and M. It doesn't care about the horizontal orientation of each other. So GM equals 1.5 feet is the same as GM equals 1.5 feet. I just chose 1.5 feet for the sake of example. But it doesn't matter where on this boat that G is, as long as it's on that same height, the GM isn't going to change. So how do we apply this to sine and cosine corrections? Well, you've seen that I mentioned in the cosine video, I suggested do your sine correction first and then do your cosine correction. Well, here is why I would suggest you do your sine correction first and then your cosine correction. When you do your sine correction, we found out that we can get our GM from the sine corrected curve, but not the cosine corrected curve. If you take your original curve given by the naval architect, perform a sine correction, then using the radian line trick, you can get your GM, so you get yourself to this point, and then you can do your cosine corrected curve to get your actual, the situation that you have on the ship. Under that loading condition, you get your righting arms. You can't get your GM using the radian line from a cosine corrected curve. However, before you even do that cosine correction, the GM is going to be the same. Remember, a cosine correction is just that perfect horizontal shift in the center of gravity. So this cosine correction doesn't affect the GM at all. So do sine correction first, get your GM, then do your cosine correction, and get your actual curve of statical stability. All right, so that does it for Lesson 5 of Chapter 4 in the Damage Control Assistant Senior Enlisted curriculum. So in the next video, it's going to be a relatively lengthy video where I use an Excel spreadsheet that I put righting arms for some fictitious vessel into, and we're going to draw that curve, the statical stability curve, and see how sine and cosine corrections affect that curve. We're going to see angles of lolling, we're going to see angles of list, we're going to see all these things I've talked about in the previous 5 videos come to life. But until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.